Greetings Astronomy 10, and welcome to your first of two lecture videos on Chapter 12, that is, the evolution of main sequence stars. Excuse me. Now if we think back to our picture of star formation, the mechanism by which stars have evolved up to the point where they actually become stars, we start with a nebula or a molecular cloud, a big ball of gas, mostly hydrogen and about a quarter of it helium with a smattering of some other objects if it's from an older generation of stellar processing, old stars have died. What happens, of course, through possibly supernova or some other momentum imparting phenomena spurring on some gravitational collapse, free fall contraction, whatever you want to call it. Eventually, the cloud of gas, this molecular cloud, nebula, whatever you want to call it, will eventually begin to condense, and due to conservation of angular momentum, it flattens out into a disk, and when enough matter falls into the center, it becomes a protostar, and the disk of matter, around it, we call that an accretion disk. Eventually, the protostar condenses, becomes denser, hotter, it emits light from its own heat, and if it becomes dense enough, the gravitational pressure in the core will be sufficient for hydrogen fusion reactions to occur, right? We have hydrogen fusing together to make helium via interactions like we discussed previously, the proton-proton chain, where you start essentially with 4 hydrogens and you end up with 1 helium. At that point, of course, once a star begins fusing hydrogen into helium, undergoing hydrogen fusion reactions, right, it becomes a fusion reactor. At that point, the protostar becomes a star and joins the main sequence, where it will spend about 90% of its lifespan as a star. This is the beginning of what we call its evolutionary track. And if you look at, let's see, it's in today's image bank. I think it's the 5th image in today's image bank. There's a nice image of where stars begin. Generally, they start larger, right? A protostar is usually larger than the star that the protostar becomes. And because it has such an increased surface area, usually they're brighter than when they're a main sequence star. Although they don't stay that way for very long. You're talking at that point about an object that already has a massive gravitational pull, right? We're talking about a system that already has, an accretion disk and lots of angular momentum and lots of gravity, right? And eventually, the gravity is going to become strong enough that it collapses into a star. That doesn't take long compared to the lifespan of a star. If you remember, stars like our sun burn for something like 10 billion years. And smaller ones can even last longer, something like 50, 55 billion years, class M stars. Now, just like class M stars versus our own class G 2.5 or so star, the sun, and class O stars and B stars, they are all different, right? Because they have varying amounts of mass, they have varying amounts of gravitational pull, and therefore have different amounts of pressure in the core, and therefore generate different amounts of energy. And so it's no small wonder to think that they have different sizes, different radii, different amounts of surface area, and emit different amounts of energy per unit of surface area, right? Bluer and hotter, etc. for the larger ones, and dimmer and redder for the smaller ones. And so essentially, a star's evolutionary track, much like its spectral profile, right, its spectral signature, is determined by the mass of the star. And so we're going to examine how stars evolve off of the main sequence beginning with the low mass stars. Mostly all stars kind of start before they're actual stars. They're large, but they're not very hot, right? And so they're, while they may be several times the radius of the sun, they're usually kind of redder, right, and dimmer before they become a star, right? Protostars usually aren't as hot because they haven't started generating energy via thermonuclear reactions. In any case, we're already aware, therefore, that there's a relationship in between the mass of a star and the luminosity or the brightness of a star for main sequence stars. But as it turns out, there's almost an exact correlation, an exact mathematical correlation in between the two phenomena. And we usually say that the brightness or the luminosity is proportional to the mass to the 3.5 power, or 3.5 as it's written in the book. Now the luminosity, if you remember, is exactly equal to the amount of energy that is generated by the star, right? The energy that's given off by the star has to equal the amount of energy that's generated in the core. Otherwise, if that were not true, then the energy in the core, if it was more than what was released at the surface, then the star would build up energy, right? And it would blow up and blow off its outer layers or something, right? And if it wasn't enough, then it would collapse. So there has to be an exact balance in between the amount of energy generated in the core and the amount of energy that the sun, or the star in general, right, any star gives off. That's, of course, not to be confused with hydrostatic equilibrium, meaning the amount of energy that's given off in the core has to balance with its gravitational pressure. In any case, because we know how much brightness a star has, how much luminosity, how much energy it's giving off, we know how much energy it's generating, right? And if we know how massive a star is, we know how much matter it has, not only in the entire body of the star, but also in its core. And that's where the fuel that all that hydrogen burns into helium is, right, in the core of the star. And so if we compare the amount of energy that it's giving off to the amount of fuel reserve that it has, right, the amount of hydrogen that it can burn into helium, we should be able to determine exactly how long stars are going to live. And indeed, if you look at the working it out, the box, whatever you call it, it's not a table, it's not really a sample problem so much, but we should be able to get some idea of how astronomers and astrophysicists have calculated the expected lifetime of different spectral class stars. If we want to compare to, say, the sun, right? The sun is supposed to live to 10 billion years. That's 10 to the power 10 Earth years, right? And the sun has one Earth mass, or I'm sorry, one solar mass, and exhibits one solar luminosity. And so from that, we're able to sort of draw this relationship for stars like our sun. But if we compare that to, say, another star that's not nearly as bright, and I believe the example that the book gives is a class K5 star. The higher the number, the dimmer, right? And of course, the OBA of GK and the spectral sequence will give us an idea of how bright and hot the surface of the star in question is. So we're talking about a class K star that's dimmer than the sun. The sun is a class G, right? It's actually G 2.5 or so. In any case, a K5 star has about 2/3 or so the mass of the sun. And so it has about 2/3 the mass, or the 2/3 of the fuel reserve that the sun has. But also, it's dimmer. And if we compare its brightness to its fuel reserve, we can see that a K5 star should have almost 3 times the lifespan of our own sun, even though it's about 2/3 the mass, right? doesn't burn through its fuel as quickly, and as a result, it has a longer lifespan. Now, that doesn't mean that all of the hydrogen in the star is going to be burnt up, and then, in a few billion years, there's not going to be any hydrogen left in the universe. Fortunately for us, it doesn't quite work that way. But pop quiz, when all of the hydrogen in the core of a star reacts, what does it become? Well, according to our models, as soon as, or as long as a star is on the main sequence, it's taking its hydrogen fuel and burning it into helium, right? And so what happens to all the helium in a core of a star? Well, the core of stars on the main sequence are generally not hot enough, not pressurized enough, in order to take helium and burn it into something else. And so that helium just kind of builds up in the core of the star. And for that reason, we call it helium ash. Kind of like, what happens in a bonfire or, at the end of a cigarette, which, by the way, don't smoke, it's gross. Now, if we want to compare that to, say, the sun, right? The sun has about half of its helium, or half of its hydrogen reserve in its core still. So that means it's supposed to live for about 10 billion years. It's burned up about half of that, so it should burn for another 5 billion years or so. Now, when a star like our sun burns up all of its reserve fuel, what's going to happen? Because that will happen someday. Granted, we're not going to be around or whatever. And it's going to be a long time in the future. I don't know about you, but I don't have 5 billion years to wait around for the sun to burn out. But when all of the hydrogen fuel in the core is used, when it's all burnt, right, and burnt into helium, what's going to happen? Well, when a significant amount of helium has built up in the core, it's not going to be able to fuse into any heavier elements in order to release energy, like the proton-proton chain fuses hydrogen into helium. And that's what generates the energy for, a star like our sun. And so that helium is just going to build up and build up and build up until there is a really truly significant amount in the core of the sun. Remember, only in the core, only in the very innermost 20% or so of the solar radius is there sufficient pressure for these thermonuclear reactions to occur. So what's going to happen to that helium, because it's not reacting, because it's not doing anything, is it's going to get smashed together. And it's going to get smashed down together into a state that it can't normally get into. If you think about the amount of pressure and temperature and the energetic reactions that are going on inside the core of a star like our sun, the individual gas particles are kind of bouncing around all over the place. They're moving relative to each other. They're knocking into each other, right? Because there's just so much temperature there that they have a tremendous amount of kinetic energy. However, the helium, because it is not reacting, and because eventually there's going to be so much of it in the core, it's going to crunch down into a state of matter that's not normally possible. We call it degenerate matter. Now, in order for us to really truly understand what we mean by degenerate matter, it sort of behooves us to discuss the nature of matter and its structure. And if we think about every element on the periodic table, all of them, they all occur electrically neutral in nature. That is, they have the same amount of protons, or positive charges, as they do electrons, or negative charges, right? They have the same number. That is how they occur in nature. There's also a third particle, of course, the neutron, and those are neutral, right? They don't have a charge, right? They're neither positive nor negative. even though they have a tiny dipole moment, but we're not going to go there. In any case, protons and neutrons are massive, right? They're both about 2,000 times or so more massive than the electron. Electrons live outside the nucleus of the atom in these complicated orbital structures, right? And the angular momentum quantization of these orbitals has given rise to the structure of the periodic table. Indeed, it's only because of quantum mechanics that we have modern chemistry and the periodic table in our understanding of it. But we won't go there either. Instead, let's talk a little bit about the nucleus of the atom for a brief moment. Protons live in the nucleus, right? The positive charges. And they're held together, of course, by the strong nuclear force, this thing we call the Yukawa potential. Now, it just so happens that if there's too many positive charges in the nucleus of an atom, they can push each other apart, and so sometimes for more massive elements, there have to be a certain number of neutrons inside the core of the nucleus, or inside the nucleus of the atom, in order for it to remain stable. But there's a danger there too. If there are too many neutrons, then the strong nuclear force can't hold it together. And that's why, like, there are some, if you want to take carbon, for example, carbon-12 is stable, but carbon-14 is not. And so, too many neutrons, too few neutrons, and, you know, it messes up the delicate balance of the strong nuclear force versus the electromagnetic force interaction. And that's why some isotopes are stable and some are not. In any case, protons and neutrons occupy a tiny little space in the middle of the atom, the nucleus. And the electrons occupy this enormous space where these orbitals are, outside of the nucleus of the atom. And electrons are sort of funny creatures in that they appear to be everywhere in their electron orbital all at the same time. And if we wanted to compare the size of electron orbitals to atomic nuclei, there's a tremendous disparity between the two. If we wanted to talk about, say, the hydrogen atom, remember that's our simplest atomic structure, that's just one proton and one electron. The hydrogen atom, in the ground state, that's the lowest possible energy level for the electron, right? And if we wanted to talk about how far that ground state orbital is from that single proton, it would be like comparing the size of a penny to the size of the moon. Of course, the ground state orbital would be the moon, right? And the single proton, the hydrogen nucleus, would be the penny. So normal matter is mostly empty space, right? You have a penny and then you have an empty cloud the size of the moon. And that's just the hydrogen atom. Granted, about 75% of the universe is hydrogen, and so about 75% or so of the matter in the universe is structured kind of like that. Now normally, that's kind of what matter looks like. And normally, atoms, even if you have a hydrogen gas in a very dense, very gravitationally, I don't want to use the word oppressed, but in a region where gravity is very strong, even then the individual particles are kind of moving around relative to each other. But degenerate matter, for say the helium ash that accrues in the core of a star, forces the atoms to kind of stack up in nice neat rows. It's like if you took a bunch of Legos and you tried to smush them all together, right? They just kind of end up all funny. But if you snap them all together in place, you wouldn't be able to stack them any closer than that, right? And so Degenerate matter is kind of like when you take all of your Legos out of the bag and you snap them all together to make one really, really small chunk, right? You can't compress it any more than that. And normal matter, even for a gas that's in a high gravity regime, like in the core of the star, that would be kind of like taking all of the Legos and trying to smash them together without snapping them in place. And so it's probably no small wonder to think that when helium atoms become degenerate, right, when they're tightly packed together such that they can't get any more tightly packed together, that it becomes resistant to compression, right? You can't push it down any farther than that. Now, it's not just the helium nuclei that get like that. Each individual helium nucleus will be bombarded with tons of electrons from all the free electrons flying around in the core of a star like this. And so the electrons in each individual atom are going to stack up first in the ground state, and then the next orbital and the next orbital, and they're going to be packed down on top of each one of these atoms as tight as they can be. And that becomes kind of an issue, because if you're one of these electrons and you want to get excited into a higher state, right? It's almost impossible, because you would have to jump, not just 1 or 2 energy levels. You might have to jump, 13 or 14, and that's a tremendous amount of energy. And essentially, these electrons are incapable of absorbing any energy or becoming excited while the helium atoms are in this degenerate state. And so we say that these helium atoms are electron degenerate. And when matter becomes electron degenerate, it gets super tightly packed and becomes resistant to compression, right? Like the difference between trying to squeeze Legos together and snapping together and pushing them down, or like the difference between trying to squeeze styrofoam and trying to squeeze adamantium, the stuff that Wolverine's claws are made out of, or titanium, or pick your favorite hyper dense, super tough, very rigid metal. Now, there's a very important principle in quantum mechanics called the Pauli exclusion principle, and that states that no two electrons can occupy the same energy level. But even in the graphic for degenerate matter, it shows that there are 2 electrons in each possible state, right? And we reconcile that with the knowledge that while we know that there are 2 electrons in each orbital, even in the ground state there are 2, right? There's always 2 electrons per orbital. We reconcile that by reasoning that the 2 electrons are actually in slightly different energy states, because their spin states, are opposite each other. And that's because there's a slightly different amount of energy from what we call spin-orbit coupling, right? So they're either spinning with their orbit or against it. Usually we say that one electron is spin up, right? It'll rotate this way. And we usually use what we call the right-hand rule, right? If you remember the right-hand rule from the Lorentz force. We use the right hand, and if you curl your fingers, right? Let's say the electron is rotating this way, right? This is its spin direction. Your thumb will give you the direction of its angular momentum vector, right? Or its spin direction. So we'd say this was spin up, and if it's spinning the other way, it's spin down. And so in any given electron orbital, one electron is spin up and one electron is spin down. In any case, that'll become important later on, and so I wanted you to have a good grasp of that. But for now, let us just realize that when the hydrogen fuel in the core of a star gets used up, the core condenses, right? All of that helium fuel condenses, or excuse me, the helium ash condenses. Let me just try to draw you a diagram of what that's going to do to the rest of the star. Meow. Meow. Okay, so here's a star. Okay, this will be like the photosphere out here, and the chromosphere, right, out here at the very edge. And then we'll draw the boundary of the core like this, like a dashed line. Okay, that's the region of the star where hydrogen is being fused, right? It's undergoing nuclear fusion into becoming helium. And what's going to happen is a bunch of helium is going to deposit here, right? Now when that helium shrinks down from, let me try to draw it this way maybe. So let's say that this volume is helium, right? And when it becomes degenerate, it's going to shrink down into this volume. That little circle in the middle, right? This volume is going to shrink down to become this volume. And that's going to essentially leave a tremendous amount of void space. But you can't have void space, you can't have a vacuum inside of a star. There's, a star like our sun has like 2 times 10 to the 30 kilograms of matter, right? And you have this tremendous amount of gravitational pressure. And so what's going to happen? Well, the rest of the core is going to move in to fill in all of this volume, right? And that means that more matter has to come in from elsewhere in the star. And that's going to cause, while I'm going to draw the center in blue now. So this part, that's going to be where our helium ash is, right? Our degenerate helium. That's not going to be burning anything. But all the rest is going to be burning helium now, right? And so this outer layer, right, this helium shell, is going to continue to burn hydrogen into helium. Now, as the core, of course, becomes smaller, it gets more dense. As the density of the core increases, the pull of gravity, right, we got the same amount of matter, but now that this has gotten smaller, the entirety of the star is actually going to get just a little bit smaller. And so we've got the same amount of matter in a smaller volume. That's going to increase our gravitational pressure, right? So the pull of gravity becomes stronger. That leaves us a higher pressure in the core. That's going to cause a greater temperature, right, along with greater pressure. And that is going to cause a hotter core than there ever has been before, right? Once we have this degenerate helium in the core, right, shrinking our star down. And that, of course, is going to cause the star to heat up, generate more energy, and that's going to deposit more helium in the core, which is going to shrink the core down even more. That's going to cause even more matter to come into the core, and that's going to make the core heat up even more, and that's going to repeat sort of ad nauseum until eventually what's going to happen is that the runaway energy generation effect in the core of the star is going to become eventually too much for the star's gravity in order to be able to handle, right? And it's going to come out of hydrostatic equilibrium. And so we're going to have more energy being generated from the core than gravity is going to be able to keep in hydrostatic equilibrium. And as a result, the star is going to expand. It's going to blow up and get bigger. At this point, it becomes what we call a red giant. That's supposed to be a G. G-I-N-T. Now, when our sun becomes a red giant, it's going to increase to probably about 50 times its original radius, which means it's going to become 125,000 times its original size, its current size, right? If you're talking about the volume of a three-dimensional object, right? If you're going to increase one of its lateral dimensions by 50, if you want to figure out the volume change, it's 50 times 50 times 50, right? Because it's 3 dimensions. So 50 times 50 times 50 is 125,000. So we increase the radius by 50 times. We're going to increase the volume by 125,000 times. The sun currently could hold 1,000,000 Earths. After it blows up and becomes a red giant, it's going to be able to hold 125 billion Earths. It's a whole lot. Now, of course, because it's going to have this tremendous amount of surface area, right, it's going to be so much larger than it was before. Not 50, but 2,500, right? 50 times 50. It's going to have 2,500 times as much surface area. And so, because of the increased amount of surface area, its color is going to dim and turn red. And if you remember from Wien's displacement law, right, while sure we have an increase in energy generation, but we also have kind of a runaway increase in surface area increase, right? And so while a star like our sun might be, kind of in the middle of the visible portion of the electromagnetic spectrum, when it becomes a red giant, it's going to get redder, right? It's going to get dimmer per unit area. But it's going to be so much larger that it's going to be brighter, right? Long story short, the increased gravitational pressure causes the core to get smaller, giving the star a new hydrogen-burning shell that causes faster burning, deposits more helium at an increased rate, that crunches down and becomes more degenerate matter, and that causes more matter from the rest of the star to come into the helium burn or the hydrogen burning region. That causes a runaway energy generation effect, and that causes a star like our sun to move up what we call the red giant branch. And I think it's the 21st, maybe, image in our image bank today. Yeah. That shows where on the HR diagram this red giant branch is. It kind of moves up and sort of to the right, right? It's moving towards the low temperature side, the M-class star side, right? The redder side of the HR diagram, but it's also moving upward, right? Because the increased surface area and the increased energy generation is going to make it overall brighter. So, as a low-mass star progresses up the red giant branch, a star like our sun is going to increase about 10 times in brightness for the first half of its blowing up to become a red giant, and then about 1,000 times in the second half, right? Because we're talking about, geometric growth, right? Growth in 3 dimensions. Eventually, the core of a star like our sun is going to shrink enough and heat up enough that 2 helium atoms can make an unstable beryllium atom. And those only live for about a trillionth of a second or something like that. But remember, we're now talking about degenerate matter, where all the matter is super crunched up together, like Legos all stacked up together, right? And so if one of these beryllium atoms, while it's not stable and only lives about a trillionth of a second, it doesn't have to live very long or go very far in order to hit another helium atom, at which point it can combine into a stable carbon atom. And that, of course, will generate energy for the star, because there's a difference in nuclear binding energy in between helium and carbon. Just like there's a difference in nuclear binding energy in between hydrogen and helium, right? We generate energy by taking hydrogen and making helium. Just like we're now going to generate energy by taking 3 heliums and making a carbon. And in just a few minutes, a star like our sun will ignite all of that helium, that degenerate helium in its core, like knocking down a mess of dominoes. We call this the helium flash. And this causes the core of a star to expand. And I know it's tempting to think that when this blows up, right, because of all of this tremendous energy being released, that maybe the star is going to blow up, but it doesn't. All of the helium in the core expands and becomes non-degenerate. And instead, we're going to have helium burning now in the core of the star. That's all we've got for today. There's a link to a video of a bunch of dominoes getting knocked down from the center moving outward, kind of like what the helium flash does, right? I believe that's at a minute and 15 through the video. We'll pick it up here next time with the red giant and find out the ultimate fate of low-mass main sequence stars next time. If you have any questions, of course, you can get a hold of me through the normal channels. And I'll see you next time for Chapter 12, Part 2.